We can hear you.
Thanks. So are there any questions before we continue? Okay, then let's continue with arc length and speed. So okay. So in order to find the arc length of a curve, so let's say you have a curve in space, and you want to find the arc length, the length of this curve from, let's say, the point A until the point B over here. So you want to find this. So that's going to be the integral from A to B, and then the square root of x of t prime squared plus y of t prime squared. Okay, let me actually. Right here. So this is going to be the integral from A to B. The square root of x of t prime squared plus y prime of t squared plus z prime of t squared. And this is actually, this comes from the Pythagorean theorem. So, and one way to see it is, well, so first we can look at this as S. We can say that the arc length over here is going to be S, and smaller arc lengths. So if you go infinitely small into here, if the arc length over here is S, then a small piece over here of the arc length, that would be ds. And so if you want to write S in terms of t, meaning now the arc length would be changing in terms of t, we can write this equation. So this would not be the arc length from A to B, it would be the arc length from A to t. So we can have that S with respect to t, and now t is this point over here, and it would be moving. So you can vary t, so that would change, and it would be the integral from A to B, from A to t, of the magnitude of r prime of t, which is the same as this thing, dt. So now if we looked at the derivative of this, ds over dt, that's just going to be the magnitude of r prime of t by the second fundamental theorem of calculus. So what does this say? This says that the change of S, the change along the curve, along the length of the curve as you change t, that's going to be equal to the magnitude of the derivative, and this is the speed. And so this would also be the speed. And if we plug this over here back into here, or really if we plug this over here back into here, then we would get that S of t is going to be equal to the integral from A to t of, and then you have ds over dt, and the dt's cancel, ds. And these are integral along infinitely small ds's along the curve. You add them up, and you will get your arc length. So that's this over here. That would tell you your speed. So in order to find the arc length in general, we are going to look at this equation over here. And in order to find the speed of some vector, the speed of some particle along a curve at a given time, we can look at this equation over here. And the reason that they're similar is because that in order to find the arc length, we can take the integral of all the little velocities along the curve. Any questions about this? Okay, so let's do an example. 1 second. Okay. So with distance measured in feet, find the speed at the time t is equal to 2 seconds for a particle whose position vector is this over here. So let's do it. So first we want to look at what r prime of t is. That's going to be 3t squared minus et and 4. Okay, and then we can plug in our 2. So then we would get that this thing over here is going to be equal to 3 times 2 squared, which is 4, negative e to the 2, and 4. Okay, and now in order to find the velocity, you need to look at the magnitude of this vector, the derivative, which makes sense. If you are a particle and you want to find the velocity at of the particle at this point. So you can definitely look at the tangent vector, which would be the vector r prime at that point 2, in our case. You can definitely look at the tangent vector. The tangent vector, though, will not tell you the speed. It will just tell you the length and the direction in which this particle would be pointing if you like cut it off the curve at this point. But it's not actually going to tell you the speed. In order to find the speed, you just need to take the magnitude of the tangent vector. So that would be the magnitude of this. So same thing in our case. The magnitude of this is going to be the square root of 12 squared plus e, whatever, it doesn't matter, negative to the 2 squared plus 4 squared. And they tell us, so that's that, and then they tell us that that is 14.65 feet per second. So that's the speed of the particle at time 2. So now, one thing we would like to be able to do is we would like to be able to reparameterize the particle. Well, in general, we can imagine, so let's just go through this. So we can have, let's say, 2 different parameterizations of the same curve. And that goes back to, oh, sorry, 1 second. Okay. So let's say first, let's look at a very simple curve. This is going to be, we're going to start with the function f of x is equal to x squared. And if you want to parameterize this curve, you can look at r of t, and you can set this equal to t comma t squared. So this is the x coordinate. That means x is equal to t. And this is the y coordinate. That would mean y is equal to x squared. It's equal to t squared. And this parameterizes the curve. But there might be other ways of parameterizing the same exact curve. And here would be an example of 2 curves. So you would have 2 curves, this curve and this curve. So this is just u cubed and u to the 6. And they're both parameterizing the parabola y is equal to x squared. So this is the one that we looked at. It's the simpler one. And this one, well, in each coordinate, you're just going to plug in u to the 3. And they're both going to parameterize this parabola. And so we're going to get the same exact curve out of both. So the one thing we really want to be able to do with reparameterization is, and I'm not going to go through this example, they just reparameterize something, but the one thing that we would want to do is to turn the arc length of the curve to 1. So let's look at a problem like that. And over here, they just go through the steps of how to do it. I think it's a little, it's not that useful to look at the steps. It's much more intuitive to just look at an example. So let's look at this example and try to see how we can reparameterize a curve in order to get different arc lengths. So first they tell us, find the arc length parameterization of this helix that is traced by this parameterization. So, and that basically means they want you to reparameterize this so that the speed at any point is equal to 1. That's really what it means. Any questions about this? Okay, so first we would like to see what the velocity is at any given point over here at this point. So that would be taking the magnitude of r prime of t, and that would be equal to, and then we would have 4 negative cosine of 4t, and 4 cosine of 4t, and 3. So that's going to be our derivative. Oh, sorry, that's going to be our derivative. And then the magnitude of this, so the magnitude of r prime of t, that's going to be the square root. And then this over here squared plus this, so let's just do that. So that would be 16, 1 second, this is going to be sine. That's 16 sine squared of 4t plus 16 cosine squared of 4t plus 3 squared, so 9. The square root of all this. Now this part over here and this part is going to be equal to 1. So we're going to get the square root of 16 from here times 1 plus 9. And this is going to get us the square root of 25, which is going to be equal to 5. So now we know that at each point, our velocity is going to be 5. And we want to make it so that at each point, our velocity is 1. So the way to do that is by trying to think about what function we can plug in to this in order to make the velocity 1. And it's pretty simple. We can just put 5. Every time we see the t over here, we can just take t is equal to, let's say, s over 5. And that's a reparameterization of the problem. And then the arc length is going to be 1. So if we go here, okay, so we know that 1 second. So if you look at the same exact problem over here, so r of t is equal to cosine 4t, cosine 4t, sine 4t, and 3t. So if this is my r of t, and now I take t to be equal to 5, to s over 5, and I rewrite this, so now r of s is going to be equal to cosine of 4s over 5 sine of 4s over 5 and 3 times s over 5. And now if we look at our prime of s, well, now this is going to be equal, so this over here is going to give us a negative 4 over 5 sine 4s over 5, 4 over 5 cosine of 4s over 5, and 3 over 5. And so then the magnitude of this thing is going to be equal to the derivative of, so I'm just going to take out the 2 4 over 5, so 4 over 5 squared sine squared of 4s over 5 plus cosine squared of 4s over 5. Okay, and then plus 3 over 5 squared. And then this is going to, so this is 1 again. So this is going to be equal to 20 over 25 plus 9 over 25. And then this is going to be equal to the square root of 25 over 25, which is equal to 1. So for any point, the velocity, the way the vector is now moving, the way we parameterize that says that the velocity is always going to be 1. And then that's just using this parameterization, which we got by finding what the original velocity was at every point. Originally, the velocity at every point was 5. And so we can try to think about what we can substitute into t in order to make the velocity always equal to 1. Okay, so in summary, for the arc length, we have the equation of the arc length, which is simply it's the Pythagorean theorem of every coordinate. So you take the derivative of x, derivative of y, derivative of z, square all of them, take the square root. And we also looked at the speed. The speed would just be the magnitude of the derivative at t. So for example, a question that can appear on the quiz might be, let's say you have two curves. So let's say you have two curves, and they intersect at the origin. So here's one, and let's say here is another. And I want to find the angle between them. So this would be R1 of t, and the red one would be R2 of t. And then the two curves have an angle, and I would like to find the angle between them. And would anyone want to suggest a way to do this? Any ideas? You guys can hear? Yep. Oh, yeah.
Find a tangent line vector and then cosine, dot product.
Yeah. So what you can do exactly is find the two tangent vectors, this tangent vector and this tangent vector. So this one would be R1 prime of t at 0. So R1 prime at 0. Let's say they intersect at t is equal to 0. Not at the origin, but at t is equal to 0. Okay, so this would be that. And then this over here would be R2 prime of 0. Those would be our two vectors. So now going and looking at this, so here's one vector and here's another vector. And asking for this angle is the same way as asking for the angle of these two vectors. So we would want to know that angle over there. And we know that that angle is going to be equal to cosine inverse of the dot product. So R1 prime of 0 dotted with R2 prime of 0 over the magnitude of R1 prime 0, R2 prime 0. Okay, so this is a type of question that it can appear. It uses things that we already know before, the dot product, how to find angles, but it also uses new things that we just learned, like how to find the tangent vector of different curves. Okay, and then we talked about how to reparameterize the length of a curve in order that the velocity be 1. Okay.
Professor,
Yep.
can you go over again why the magnitude of the tangent vector can be the length of the S?
Yeah. So just looking at the equations. Yeah, definitely you can say if you write S of t to be equal to this over here. So here S of t is equal to the integral from a to t of sorry, 1 second. Yeah, of r prime of u du. And now ds. So that, yeah, we're just saying that that's what S of t is, and ds over dt, that's going to be this, and this is the speed. The magnitude of the velocity, I would say, you can pretty quickly intuit or accept that that's going to be the speed of the particle at the point t is equal to whatever. And so if this is going to be your speed, well, what is the way to find an arc length? You can add up all of these. So 1 second. If your S is your length, I'm honestly not 100% sure that this would, I mean, you can use the fundamental theorem of calculus. In general, the fundamental theorem of calculus connects these like velocities to the arc length. I would actually say, in general, a better way of seeing how you can get this formula is by looking at this graph over here, and let's go. So let's say you have the curve, and you want to find the arc length from A to B. So we can, for every point over here, we can have a dx, a dy, and a dz. Forgetting about the parameterization for a second. And if you look at dx squared plus dy squared plus dz squared, and you take the square root and you take their integral from a to b. Well, naively speaking, if you can say what this is exactly, this would be the length, because you have your x direction, the length of your x direction squared, plus your y direction squared, plus your z direction squared, and you're taking the square root, and you're taking the integral. The problem is, what's the integral in terms of? Like, we would like it to be in terms of t. So let's multiply this in terms of dt. And then let's put it inside. So actually, doesn't matter. But let's put the second dt and dt over here. But let's put this dt inside. So that would be this over dt squared, and this over dt squared, and this over dt squared. So that would give us the integral from a to b square root of dx over dt squared plus dy over dt squared plus dz over dt squared dt. And that's what we have, right? And this is equal to the same thing as AB of the magnitude of r prime of t. So that's what we have. And then you can go the other way. Once you know that this is your arc length, you can figure out the speed, because the speed at some time is going to be the change along your arc length as you change t. So that's going to be your speed. And yeah, this formula just comes out of the Pythagorean theorem, but looking at dx, dy, and dz instead of actual lengths. Yeah, does that make sense?
Yeah, thank you.
All right. So now let's continue to curvature. Okay. So the curvature is, in general, we're going to try to, you see this has a lot of curvature. It's curves a lot. And this has some curvature. Again, it's curving. Lines don't really have curvature. And we would like to be able to tell or to find a formula to calculate the curvature of some curve. That's the point. And so we first start by just mentioning what the unit tangent vector is. It's just going to be that. It's the tangent vector over the magnitude of the tangent vector. And here's an example for how to find the unit tangent vector at some point P. If r of t is equal to this, r prime of t is equal to this, the unit tangent vector at some point, well, we just plug in that point and we get 1, 1, 1. Or do we? 1 second, 1, 2. No, we get 1, 2, 3. And then we divide by the magnitude of 1, 2, 3. R1. Oh, okay, doesn't matter. Okay, so that's how to look at the unit tangent vector. And then in order to define curvature, this is just the definition. You cannot use it to actually compute curvature. You're going to look at how your tangent vector changes as you change s. So here's your curve. You vary your s. So s is inside. You see the ds. You can actually write that out as the square root of dx over dt squared plus dy over dt squared plus dz over dt squared. And so these, the dx, dy, and dz, they're kind of pointing out of the curve. So whatever they would be, the dx would be in the x direction. So it would be the amount that the curve moves in the x direction. The y would be the amount that it moves in the y direction. And the z would be the amount that it moves in the z direction. But the ds is the amount that it actually, you can imagine sitting in the curve, and here is your length, the amount that small moves in the length in the curve, that's your ds. So this would be your ds. Maybe actually ds does not have the t's, something, I'm not sure, whatever, you can actually just figure out. But anyway, and so then the curvature is going to be the change of your tangent vector over the changes of s. So here, imagine here are all your unit tangent vectors. And we vary s a little, so we move s a little, and we see how the tangent vectors change, and that's going to give you your curvature, which makes sense. It would pay attention to how the tangent vector is changing, and that type of change will tell you about how curvy something is. If the tangent vector is not changing, if you're on a line, the tangent vector always goes in the same direction. So as you move s, your tangent vector does not change, and so this would be equal to 0, and your curvature would be 0. And so then what they do over here is they try to use this actual definition in order to compute the curvature of a circle. And I'm not going to go through that because you don't need to know how to do that. All you need to know is how to use this formula. So don't try to compute curvature by looking at the definition. This over here is just a formula that allows you to compute the curvature of a curve that has been parameterized. So it would, and in general, you would be computing it at some point. So let's say you want to compute the curvature for t is equal to 0. So you would go, well, the curvature at 0, for t equal to 0, is going to be the magnitude of r prime at 0. And you would put this in. So it would be a vector with numbers cross r double prime 0 over the magnitude of r prime 0 cubed. And that would be your curvature. And over here, they prove why that is. We're going to not do that. Okay, so now they want us to actually compute this. 1 second. Okay, so calculate the curvature of this twisted curve. And, okay. T squared, t to the third. T squared, t to the third. So this is my r of t. And the curvature is going to be equal to the magnitude of r prime of t cross r double prime of t over the magnitude of r of t cubed. Let me just, yeah. So what is r prime of t? That's going to be equal to 1, 2t, 3t squared. What is r double prime of t? That's going to be equal to 0, 2, and 6t. Okay, so now r prime of t cross with r double prime of t, that's going to be equal to the determinant of the matrix I, j, k, 1, 2t, 3t squared, 0 to 6t. So this is going to be equal to I times 12 t squared minus 6 t squared minus j times 6t plus k times 2. And so then this is equal to the vector 6t squared negative 6t and 2. Yeah, so that's correct. And so then you can take the magnitude, and the next couple of steps I'm going to, well, leave for you, I guess. But yeah, anyway, you can find the magnitude of the r prime cubed, and that would get you this, and that's going to be your curvature. And you can plug in your different t's to see what your curvature is. Okay. And now this formula over here is just going to take this formula and simplify it. So it's just looking at this formula, it's simplifying it for the case of a plane, I would say there actually is not a good reason at this point to learn it specifically. Just use the previous formula. Okay. And over here, they're wanting to find the curvature again of a graph of a function. Again, it's a simplification from the previous formula. So again, not important to like look at this one specifically. Just look at the previous formula. Okay. So any questions about this so far? Okay. So now another vector that we can look at is the derivative. So it's the normal vector, and it's the derivative of the tangent vector over the magnitude of the tangent vector. So here's your tangent vector. If you take the derivative and you take the magnitude of the derivative, you get a vector that's always orthogonal to the curve. So if here's your curve, so here's your space. Here's your curve. Your normal vector is going to always be orthogonal to this curve. And it's going to equal to the derivative of the tangent vector over the magnitude. Okay. So here they ask us to find the normal vector of the helix, 2 cosine of t, 2 sine of t, and t. So r of t is equal to 2 cosine of t, 2 sine of t, and t. So first, how does this thing look exactly? It would be x, y, and z. So in the x and the z direction, if we think about the t direction as z direction being 0, this would be a circle, right? Because you would have this squared plus this squared. So if this is your x and this is your y, then x squared plus y squared, well, that's going to be equal to 4 cosine squared of t plus 4 sine squared of t. Just plugging these in, and that's going to be equal to 4. And because of that, we get this relationship, x squared plus y squared is equal to 4. So this is going to be a circle with radius 2. And that's in the xy coordinate if your z is 0, so it would be a circle. But because that the t is not 0, you can actually think about this as a helix. So here's our helix. And it also does the same thing going down. Okay, perfect. Now we want to know the normal vector of this helix. So let's first find r prime of t. So r prime of t is going to be equal to negative 2 sine of t, 2 cosine of t, and 1. So now my tangent vector, my unit tangent vector, is going to be r prime of t over the magnitude of r prime of t. Okay, and now this is going to be equal to so what is the magnitude? So this squared plus this squared. So let's just figure out what r prime of t, what the magnitude is. So that's going to be the square root of 4, and then I'm just going to write 1. Sine squared plus cosine squared is 1, so 4, and then plus 1. So it would be the square root of 5. So then this over here is going to be negative 2 sine of t over 5 over the square root of 5, 2 cosine of t over the square root of 5, and 1 over the square root of 5. So let me see. So far, one second. Yeah, okay, square root of 5. So yeah, perfect. Okay, and now they just want us to find the magnitude, and that's going to be 2 over the square root of 5. Very similar steps, okay? And then your normal vector is going to be this, which we found, over the magnitude, which is fairly simple to find, and that will give you your normal vector. And so again, your tangent vectors are going to be pointing tangent to this helix at any point. So here are your tangent vectors. And your normal vectors are going to be pointing inside. They're going to be normal to the curve, or orthogonal. Okay, now we have two vectors, and here are two vectors. And we can look at their cross product, which will create a vector orthogonal to both of them. It would create that vector over there. And we call that the binormal vector. B is equal to t cross n. And this creates a frame. You have your tangent one, your normal one, and your binormal one. And so, for example, in the example that we're working on, they ask us to find the this complete frame for this curve. So like we said, the tangent one is this, the normal one is this, and the binormal one is going to be equal to the tangent one cross the normal one. So you just take the cross product of these two things, and you will get that. Any questions? So I don't think you need to know what oscillating circles are, and I don't think that would be very helpful. So I think we will stop this section here. So the only real things that we went over today is the length, finding the length of a curve, so we looked at if you have a curve R of t, then we can take the length, and that would be the arc length, and that would be the integral from a to b of the square root, or okay, whatever, of x prime of t squared plus y prime of t squared plus z prime of t squared dt, which is the same thing as the integral from a to b of the magnitude of r prime of t dt. And then we said that you can also find the speed of a vector at a certain point, and that was by just looking at the magnitude of the derivative. So the magnitude of the derivative at some point, that tells you the speed at that point. Okay, and then, one second, was that basically it for that section? Oh, and then we figured out we learned how to reparameterize a curve in order for the, okay. We learned how to reparameterize a curve in order to have that the velocity at any point is going to be equal to 1. And then, okay, 1 second. One second. I need to get my charger. Okay, and then we looked at curvature. Okay. So then we looked at curvature. We first said that the tangent vector is going to be r prime over the magnitude of r prime. The curvature is going to be the change of the tangent vector, which makes sense. The amount of the tangent vector is changing as you're moving along the line, which should tell you something about the curvature. And we saw the formula for curvature, which is the only real formula that you need to memorize for curvature: magnitude of r prime t cross r double prime t over the magnitude of r prime cubed. And then we looked at the normal vector. The normal vector is the derivative of the tangent vector over the magnitude of the tangent vector. And that gave us a vector orthogonal to the plane. And then we took a look at this frame with the binomial vector, which is t cross n. And now we have 3 different vectors, and they go n, t, and b along the curve. And sometimes it's useful to find these 3 vectors. You would only need to find them. You don't need to do anything else with them if that appears. If you need to look at curvature, they'll just tell you find a curvature at some point. You wouldn't really need to do anything with that curvature. So these type of problems are just very, computational. Just plug it into the formulas. So again, in summary, the tangent vector is the tangent vector. The unit tangent vector is the tangent vector that we looked at over the magnitude of that. The curvature is the change of that tangent vector as you change s. The formula is going to be this. We will ignore these. The normal vector is the tangent vector over the magnitude of the unit tangent vector over the magnitude of the unit tangent vector. And then the frame will add a b, which will be the cross product of the 2, and other stuff we don't really need to know. Okay, so I think we're gonna stop here. There are homeworks and stuff on all these problems. If you have any questions, please let me know. Do you have any questions?
Professor, quick question.
Yep.
Isn't the unit tangent factor, isn't the magnitude of it is 1, that's why it's a unit tangent vector? Or does it?
For the tangent vector, yeah, but we're taking the derivative.
Okay, gotcha. Thank you.
Any other questions?
Is the quiz going to be like last time we actually had like 3 hours?
Yeah. Yeah, it's going to be like 5 questions, 3 hours. Any other questions?
It's until this point, right?
Yeah, up until here, right here, including what we did today, so the curvature and the frame, the normal. You have to know how to find the unit tangent vector, the unit normal vector, and your binomial vector, and that's it.
Is Thursday going to be any review?
I think the review. No, so Thursday, we're going to continue, and I'm not going to. I'm thinking more of this quiz as like a review for this exam. We are going to review for that exam on Tuesday next week, but I'm not going to review for this quiz specifically. No. Okay. Any other questions? Okay, then have a nice day. Bye.